Well, while you're looking, just, I don't know if you've been checking your emails, but there is a short 30-minute lecture posted under week 11. They're just examples. There's no new theory, just examples on how to work those properties, because we've covered everything. There's just a bunch of examples. Kind of what I was supposed to do on Wednesday, but didn't. Did you get that email? Jesus Christ, guys. Check your Canvas emails. That was part of the note on the door, was check your Canvas email. So, did you find your question?
Yeah. Okay. So like when it says express in terms of logarithm exponents,
Right. All right, you need to slow down and speak up. Well, what was that? Log base what?
says the fourth root
M to the 8th.
over c.
Was it under the same root?
Yeah.
Like that?
Yeah.
And was there a base on that logarithm, or
Yeah.
base C? Okay. So this kind of examples you'll find in that little video that I posted last week, but here's the idea. First of all, the base is absolutely relevant in this example. Doesn't matter what base is as long as it's a log. But we have these three laws. One says if you have a log base whatever of a product, that turns into a sum. So we covered that last Monday. And if you have a log of whatever base of a division, that turns into difference of logs. And then if you have a log of whatever base of something raised to a power, that power can come down. Right? So we have these three major properties of logarithms. Okay? So operating with them, we can split this whole thing into pieces. Because what I see right now is I have a logarithm of something under the fourth root. Right? So I can express the fourth root as an exponent, can I? Fourth root is what power? No, 1 over 4. So this is the same as log base C of m to the 8th, n to the 16th over c to the 9th to the power 1/4. Just by, properties of the radicals. There's nothing new here. We covered that in 099, I think. That the radicals are fractional exponents. Well, now all I see is that I have a logarithm of something with a power. So that looks like this third property. So I can bring that power down. 1/4 comes down, and then we're left with a log of whatever's here. So that's how you deal with the radicals. You turn radicals into fractional exponents, and then you bring the powers down using that power rule. No, not even close. I have to keep going because, I still have exponents. I can dissect it into many pieces, but that's the step one. This is how you get rid of the radical. Is that okay? All right. Well, now, so I have this 1/4 on the outside. All I see is the logarithm of a division, right? Do I have a rule that tells me how to deal with the division? Sure do. So division turns into subtraction. So 1/4. Now 1/4 will still be multiplied by everything. So I'm going to split this division into subtraction. So this is log base C of m to the 8th, n to the 16th, minus log base C of c to the power 9. So the division turned into a subtraction. I still have a log of a product, right? I can do something about this little product here. So that's the first rule. The product turns into addition. So it becomes 1/4 log base c of m to the power 8 plus log base c of n to the power 16. I'm just going to copy this log base c of c to the 9th over, and then I'll just deal with all of them. So fraction turned into subtraction, the product turned into a sum. And I really recommend you guys watch that little video under week 11. It will help a lot with this. I mean, I did a bunch of examples like that. So what else can I do? Because remember, your question said no exponents, right? Okay, so do I have exponents? Yeah. Can I do something about the exponents? Yeah, I can bring them down using that power rule. So the power 8 comes down, becomes 8 times log base c of m plus 16 can come down, 16 log base c of n. Is that okay? Well, what is log base c of c to the power 9? What is that equal to? 9. That's right. Log base c of c to the 9, since the bases match, that just equals 9. Right? Since the bases matched here, we can drop everything there. Well, I think you can distribute the 1/4. 1/4 times 8 is 2, so it's 2 log base c of m plus 1/4 times 16 is 4 log base c of n minus 9/4. So now I don't have any powers. I have a lot of simpler logs. Yeah. Yep. That's not, it's not trivial, but if you take step at a time, you have this 3 laws, and we have 4 properties. The log base a of a equals 1, log base a of 1 equals 0, log base a of a to the x equals x, and a to the power log base a of x equals x. So you have them since last Monday. So basically operating with, mainly with the first 3 big things, we can dissect any logarithm.
So, are you saying base C and C cancel each other out?
Right, because of this property right here. This one.
Log base A.
Yeah. Because again, the question is, to what power do you need to raise c to get c raised to the power 9? And the answer is 9. Okay. So whatever I'll be doing today, we'll still be using these rules. It will be important for us, especially go backwards, starting with manual logarithms and putting it together into one. But the homework and the quiz that's due tonight, there are sections 5.3 and 5.4, so that's what this is. And really watch that little 30-minute thing. It will help. All the secrets. Oh yeah, just 30 minutes of examples. You're not asking questions. Man, I went supersonic. There's like 20 problems. But some of the, starting with some simple ones and getting through through something like that. There are examples like that at the end. If I pull this up, I'll just show you. They have a new website. Is that a new website? How do you get on? Okay, here's Canvas. It's nice. So in your class, so under week 11, so here we go. You have a little video, just examples, and just to show you, these are just the nodes. There are 9 pages worth of stuff. But, so here we go. So a bunch of problems like we just did. Yeah, right. And there's a video as well. Yeah. It's about 30 minutes. So anyways, you can watch it at home. So anyways, so we're going to start solving equations today. Section 5.5, sorry. So 5.5, solving exponential and logarithmic equations. So I'm just going to start with an example, and then we'll just talk about this. If I have something like this, so this would be an example of an exponential equation, 2 to the power negative 2x plus 1 equals 2 to the power 4, for example. So this is an example of a exponential equation. Our variable is an exponent. And what makes this equation nice is that the bases on both sides of this equation are the same. Okay? So the bases are the same, and the one big thing that we know about exponential function is that it is one-to-one. What that means that each height is reached exactly once. You cannot reach the same height more than once. Like a parabola, you can get to the same solution on different x values. With exponential function, it doesn't work. Each solution is reached once on the graph. So in order for this equation to work, the exponents have to be the same. What do you think of that? Yeah, so the bases don't even matter in this case. If the bases are the same, then in order for me to solve this equation, all I have to make sure that exponents are equal. And that's it. If bases are the same. Now this is a very simple linear equation, right? We can solve it. Subtract 1, negative 2x equals 3. So x equals negative 3/2. And that's it. We're done. So we're using this, your book calls it base exponent property. What this means, if bases are the same, then exponents have to be the same. So if a to the power n equals a to the power m. That implies that n equals m. Okay. So let me do a few examples. Let's say 2 to the power, well, how about 4 to the power x squared minus x equals 4 to the power 12, negative 12. Yeah. Again, the second you see that bases are equal, that's the big thing here. If the bases are the same, then exponents have to be the same, so you can ignore the bases. The base 4 is irrelevant in this case. I could have put base 14, base 12, as long as it's equal. Right away, I can go ahead and say x squared minus x equals negative 12. And then solve that equation. That's a quadratic equation. We can solve that. X squared minus x actually should have been positive 12, as I originally was trying to do. Otherwise, it won't work. So then it's minus 12 over here equals 0. So then it's easy to factor and all that stuff. Okay? So that's easy to factor. That's x minus 4, x plus 3 equals 0, which gives us two solutions. What? Out. And that's it. So this equation has two solutions. But again, if I plug in 4 in for x, I'll get 4 to the power 12 equals 4 to the power 12. And if I take negative 3 and I plug in for x, I'll get 4 to the power 12 equals 4 to the power 12. So both things solve that equation. How's that? Yeah. Those are the only two possible solutions to that equation. Okay? And again, this seems pretty simple, but it's only the case if bases are equal. If what left side was 4 to the power x squared minus x and the other side was 5 to the power 12, I have to get more creative. But if bases are equal, then you just make exponents equal. Does that make sense? Okay. How about this one? 4 to the power x equals 32 to the power x plus 1. Well, you're right. Why it doesn't work? They're not the same, but right, I can tweak it a little bit. I can express number 4 and number 32 in terms of the same base. Right? I can think of 4 as 2 squared. Don't you agree that 2 squared is 4? So still raised to the power x. Well, I can think of 32 as 2 to the power 5. Still raised to that. Do you agree that this is the same as the original problem? I just express 4 as 2 squared and express 32 as 2 to the 5th. Then by the rules of exponents, I have to multiply the power. So that becomes 2 to the power 2x equals 2 to the power, when you multiply that by 5, is 5x plus 5. Right? We'll multiply exponents in those cases. Well, now we're back to having the same base. So it's back to the original type of problem. We can just equate exponents. 2x equals 5x plus 5. And then just solve for x. That's a simple linear equation. All right, so whatever, how you like to solve this one, it's up to you. So negative 3x equals 5. So x equals negative 5/3. There'll be a solution to that equation. Any questions on that? So sometimes you can tweak the bases so they're equal. Again, if this was 4 to the x and then 31 to the x plus 1, it wouldn't work like that. I would have to get more creative. But any questions on this?
So am I just supposed to know that 32 is 2 to the power 5?
Yeah. You should know your powers of 2 up to 10, right? 2, 4, 16, 32, 64, right? 128, 256. Because if you bought anything with memory in past 10 years, you've seen those numbers, right? 256 megabytes or 512 and all those numbers. Those are all powers of 2, right? Anyways, here's a little tricky problem. 27 equals 3 to the power of 5x times 9 to the power x squared. Well, you have to be very careful here and not, try not to violate orders of operation. Because again, the only way we're going to make these equations to work right now if both left and right sides expressed exponentially with the same base. Okay? So which base do you think we'll be going for? 3. Because on the left, 27 is just 3 cubed, while on the right, I have 3 to the power of 5x, while 9 is same as 3 squared to the power x squared. Right? So then I'll play with my rules of exponents. The rule of exponents tells me to multiply powers. So this is 3 to the power 3 equals 3 to the power of 5x times 3 to the power 2x squared. Is that okay? Now, on the right, when we multiply expressions that have the same base, what do we do with exponents? Add them. So that becomes 2x squared plus 5x. So just after playing with exponents, we got to this point. Nothing new really here. This is just using the old rules of exponents from earlier courses. But now we have same basis, so we can just go ahead and set powers equal to each other. So this becomes 2x squared plus 5x equals 3. Right? Which is a quadratic equation. Get everything on one side. We can factor this one, right? I think so. 2x minus 1 and then x plus 3, that's right. Or use the quadratic formula, it's up to you. And after setting each factor to 0, we get x equals 1/2. X equals negative 3. How's that? I agree, it's not too painful. Actually, it won't get too the increase in the amount of pain you'll get from that won't be that dramatic, as usually. Well, he said it's not that painful. It will get more painful, but not that much. Because again, this is a nice case where you have the same basis. Okay? It's not so nice when you don't have same basis. Because I mean, you don't need anything new that we just learned to solve these types of equations. Just kind of get them on the same base, make exponents equal to each other. But if I give you this one, let's say 3 to the power x equals 8, and we kind of solved that one already just by playing with logarithms, expressing this equation in terms of a logarithm and then using a change base formula. We've done that. But what I can do now is just apply logarithm to both sides, because we have, since both exponential functions and logarithms are 1-to-1, we have the same property as with the exponentials. I mean, if you have identical logs, same base, then the inside have to be the same, just like with the exponents. So that allows me to take a logarithm of both sides and use a calculator. And since that's the option here, you only have really 2 logarithms to choose from, base 10 or base e. If I take log of both sides of this equation, because that thing allows me to do that. Now the rule that we just reviewed at the beginning of the class, if I have a logarithm of something with a power, what happens to that power? Yeah, I can bring the power down, so that is x times log of 3 equals log of 8, which is now a linear equation. I can solve for x. X equals log of 8 over log of 3. And we're done. Which is a change base formula, really. Because if I express this as log base 3 of 8, then change base formula will just give me that. So anyways, you just plug in your calculator. Log of 8 divided by log of 3, so 1.89-ish. Okay. So how is that? Does that feel good? All right. Let's do a few more.
So you can do it why don't you just take the log of, like, why did you do that rather than what you were doing?
Well, because I cannot turn 8 into 3, right? Well, how about this example? It's a little messier. 28 to the power x equals 10 to the power negative 3x. Okay? So again, the exponents are unknown. We have 2 variables on both sides of the equation, and there's no way you can tweak 10 and 28 to have the same base. So we're going to end up bringing those powers down by the means of taking logarithm on both sides. And here's the big thing. I mean, you can take any log that you like. You can take natural log, you can take log base 10, you can take log base whatever your favorite number is. But if you already have a 10 as a base here, it already appears. So really using log base 10 would work really well. Because remember, taking logs with the same basis will just eliminate, right? That just kind of cancel each other. Is that property right here? Because again, we solve equations, we're only going to be operating with a natural log or base 10. Because that's all our calculator is capable of doing. So if you already have a base 10, then really take log base 10 on both sides. If you had an e anywhere in there, take natural log of both sides. Otherwise, it'll get a little harder. So since we already have base 10, take log of both sides. So this is what will happen. If you take log what will happen on the left, x will come down, x times log of 28. Okay, so that's using the power rule. Exponent comes down. Now on the right, you have same bases. So that's one of those inverse properties. You're just going to end up with negative 3x. Okay? It's a silly problem.
That's because of which problem?
The thing on the right? Well, this is that one right here, the inverse property. When you have a base of the logarithm matches the base of the exponent. So to what power, because basically again, the question is to what power I need to raise 10 to get 10 to the negative 3x. It's negative 3x. So again, we ended up with linear equations. So how do we solve a linear equation? How do you solve linear equations? If you have variables on both sides of the equation, what do you want to do? Well, you want to get all the variables on one side, right? That's what you want to do. You want to get all the variables on one side. So in this case, yes, it will get set equal to 0. So on the left, you have x times log of 28 plus 3x, while on the right side, you have 0. Now, when you solve linear equations, usually you don't end up with something like that. You're usually actually able to add both numbers. Here you can't really add them, but what you can do, you can factor the x out. Okay, you can do that. You can get, all right, if you pull the x out, then you have log of 28 plus 3 equals 0. Right? Now again, with the linear equations, on one side you have a variable times a constant. How do you get rid of that constant? Yeah, divide. So divide by whatever that constant is, log of 28 plus 3 on both sides. Well, 0 divided by whatever is 0, so actually x equals 0 is the solution. Yeah, but the process would be the same. Just if you think about this, I'm going to give you an example. Don't write anything down. But if this was your problem, let's say 2x minus 3 equals 4x minus 3. How would you solve this equation? Get the variables on one side, get the constants on the other side, right? So you would subtract 4x and add 3. So here you have 2x minus 4x equals 0. So this is kind of this step right here, right? Now, luckily, with 2x minus 4x, we can easily make it negative 2x. There we cannot. But really, if you think about this, combining like terms is equivalent to factoring out and then doing the parentheses, right? So anyways, your left side is negative 2x equals 0, and then you'll divide by negative 2. You'll still x equals 0. So that's the same process of solving linear equations. The only problem here is that at times you won't be able to combine those expressions. So you have to factor the x out. Let me try this one. e to the power negative c equals 5 to the power 2c. Right, take the natural log, because you already have e in there. It will be easier if you take natural log. So take ln of both sides. So natural log of e to the negative c equals natural log of 5 to the power 2c. Now on the left, natural log of e to any power is that power, so they just cancel each other. The left side is negative c, because the bases match. While on the right, 2c comes down, and then ln of 5 stays. How's that? Again, the left side is the same property when the logarithm has the same base as the exponential. Yeah, so it's kind of the same process. So we're still going to get 0, actually, for the answer here. If you get everything on one side, it is 0 equals 2c ln of 5 plus c. And I can factor c out. And then just divide, so actually it happens to be 0 again. And yeah, and of course that works. If you plug 0 for the variable, you just get 1 equals 1, so good. Yeah, in this case. Let me try the one that you don't get 0 in the end. What if we do something like this? 10 to the power x minus 2 equals 7 2x plus 1. Okay? So we happen to have base 10 already. So which log should we use here? Yeah, the log, the common log for the base 10. So take log of both sides. So that gives us log of 10 to the power x minus 2 equals log of 7 to the power 2x plus 1. So again, the same property on the left leaves us with just the exponent. So the left side is x minus 2. While the right side, 2x plus 1 comes down times log of 7. Okay? So that's a linear equation. How would you solve that equation? Get variables on one side, but before you do that, what will you have to do first? If this was not log of 7, but just 7, what would you do? Distribute, so same thing. Log of 7 is just some number. So distribute log of 7, so we'll get x minus 2 equals 2x log of 7 plus log of 7. Just like with any other linear equation, you would get rid of the parentheses first. And now you're going to start grouping all the constants on one side and all the variables on the other side. So like that negative 2, that's just a constant. So I'm going to add 2 to both sides. while 2x log of 7 is it contains a variable, so I'll subtract that from both sides. So that cancels, so we're left with x minus 2x log of 7 equals log of 7 plus 2. Right? If you move everything that has a variable to one side, everything that doesn't to the other. Okay. So again, remember, I need to get x by itself. There's x in two places. Can't really combine like terms. So what are we going to do with that x? What? Yeah, just factor it out, just like we did before. So we're going to pull the x out. That leaves us with 1 minus 2 log of 7 equals log of 7 plus 2. So that's an x times a constant equals another constant. To solve for x, just divide by whatever's a constant in front of the x. So divide both sides by 1 minus. So x equals log of 7 plus 2 divided by 1 minus 2 log of 7. Now that's a number you can plug in your calculator. So depending on how that MyMathLab thing is asking you to put your answer in, if you have to round it and plug it in the calculator, if it says exact answer, that's the exact answer, because there's no rounding in there. But if you plug it in the calculator, you just go 7 log plus 2 equals that, and then we'll just divide that by, I'm going to use the parentheses here, 1 minus 2 times log of 7. So negative 4.12, something like that. How's that? Is that okay? What if I do something simpler? What if it just e to the power 2x equals 0.008? How would we solve that? Take the natural log, because it already has e in there. So use the natural log. Take a ln on both sides. So natural log of e to the 2x equals natural log of 0.008. So the left side identically equals to 2x. And then to solve for x, just divide both sides by 2. So x equals natural log of 0.008 over 2. Is that all right? I can plug that in my calculator. Natural log of that. So negative 2.41. Is that good? What if I change this a little bit? What if it's 1,000 times e to the power 2x equals, let's say, 5,000? How will we go about solving that one? Divide by 1,000 first. You do want to have just an exponential expression by itself, because taking the log of both sides will make it a little messy. So first, get rid of that coefficient. So it is e to the power 2x equals 5. And then take natural log of both sides and solve for x. So natural log of e to the 2x equals natural log of 5. So 2x equals ln of 5. So x is ln of 5 over 2. Whatever that is. You can always plug that in your calculator. 2 natural log, I'm sorry, 5. 5 natural log divided by 2, so 0.8. How's that? So far, so good? Okay. Well, what if I do this? 3 to the power x minus 1 equals 4 to the power 2x. I'm not even sure whether it will have solutions. It will. So we have two exponential expressions, different bases, but none of them is either 10 or e, right? Because up to this point, we only had either e or 10, but this is just random 3 and 4. So it doesn't matter which log you use. Natural log or log base 10 is just going to suck regardless, okay? But, so which log is your favorite now? Log? Should be ln. But it doesn't matter. It doesn't matter. So let's say, let's do log of both sides. I know, it's just an extra letter, right? Log of both sides. Could be ln. That's really personal preference. Doesn't matter. So if I do log of 3 to the x minus 1 equals log of 4 to the 2x, take log of both sides. So the exponents will drop down. So that becomes quantity x minus 1 times log of 3 equals 2x times log of 4. Okay? So, what do you want to do now? Distribute, very good. So just like before, distribute. So x times log of 3 minus log of 3 equals 2x log of 4. Again, if you ever get stuck with the process of solving the equations after you bring the powers down, just think of this as a linear equation, because it is. And think about how would you solve a linear equation. So what would you do next? Right, you want to get variables on one side. So you would subtract 2x log of 4, and you would add log of 3 to both sides. So this is x log of 3 minus 2x log of 4 equals log of 3. Now what? Factor the x out. Log of 3 minus 2 logs of 4 equals log of 3. And then what? Right. Divide by the big constant. So we'll get x equals log of 3 over log of 3 minus 2 logs of 4. So that's an exact solution. You can plug that in your calculator to get approximate solution or whatever. Now, plugging this number in a calculator is actually, well, if you have a graphing calculator, then just type it in with a bunch of parentheses. But if you have a normal scientific calculator like the one that I'm using here, it's going to be pretty hard to plug that number in. So you can actually do, if you want to, let me show you how to make it a little easier. If I have a number in front of the log like that, what can I do with that number? Yeah, I can put it back as an exponent, right? I mean, you don't have to do that if your calculator works well. But if you have a simple, basic calculator, you can simplify this expression into saying, well, this is the same as log of 4 squared. 2 goes back as an exponent. Now, what is 4 squared? 16. And then I see a big minus between two logs. If I have a minus of the logs, that becomes division. So this is the same as log of 3 over log of 3/16. Right? 3 goes on top, 16 goes on bottom. This is a lot easier to plug in your calculator. Just a few extra steps, because then I can just go 3 log of that divided, and then 3, I don't know if that'll work. Nah, probably won't work. It's calculators too. Yeah, it won't work. I have to go the other way. 3/16 log of that, take the reciprocal, and then times log of 3. Here we go. Still complicated. Well, I can toss 2 on top as an exponent. That becomes 16. And then a minus becomes a division, so it's 3 over 16. Oh, no, that was 4 squared is equals 16. Is that right? If you had a good calculator, -656. Okay? So any questions on this case? So different bases, 3 and 4 cannot be turned one into the other. So just take whatever log you prefer, that particular day, on both sides, and then solve the linear equation. How is that? That good? You like that? Yes? Well, let's try this one then. Well, this is bad. Yeah, let's try this one. E to the x minus 6e to the negative x equals 1. Okay. Well, we haven't seen anything like that, right? That's a problem that contains 2 exponential equations and then just a constant. So I cannot start taking logs of both sides because I do not know how to take a log of a difference. But tell me, what does the negative exponent mean? What is the interpretation of negative exponents? Anyone? Reciprocal, thank you. So this is the same as e to the x minus 6 over e to the x equals 1. Right? Okay. So that all of a sudden became an exponential equation with variables in the denominator. So this is kind of like equation that involves rational expressions when we have variables in the denominator. What did we do when we had variables in the denominator? What was the trick we used to make us happier? if we have variables in the denominator? How do we get rid of variables in the denominator? Multiply by what? Well, by the whatever the common denominator is, which in this case, just e to the x. I'll multiply both sides of this equation by e to the x. You're going to love this problem. It really tests you on everything you've done. So e to the x times e to the x is what? No, it's something times itself. E to the x squared, but it's written like this, e to the x squared, right?
Multiplied by those.
Right, which is just,
You do it to get rid of that.
yeah, to get rid of the denominator, because what will happen here, the e to the x's will cancel, so you're just left with negative 6 equals e to the x, right? Now, if I move everything to one side, e to the x squared minus e to the x minus 6 equals 0. It looks like a quadratic equation. Very good. It's one of those equations of quadratic types, right? That's when we'll make our little substitution. You can do that. You can say, let u equal e to the x. So then it just becomes u squared minus u minus 6 equals 0. So this looks quadratic. Well, that one is easy to factor. That equation factors into u minus 3, u plus 2 equals 0. So that means u minus 3 equals 0, or u plus 2 equals 0. So u equals 3, u equals negative 2.
And you just say e to the x equals.
Right. Very good, because you need to substitute back. So yes, it is e to the x equals 3, or e to the x equals negative 2. Question? Okay. So how do you solve e to the x equals 3? Yeah, natural log, so it actually means x equals ln of 3. If you take natural log of both sides. Now, on the right side, e to the x, what is the range of exponential functions? Just think about the graph of exponential function. What is the range of exponential functions? 0 to infinity, so it cannot be negative. E to the x equals negative 2 has no solutions. So this one has no solutions. Even if you try, even if you write it as a natural log of negative 2, and you plug it in your calculator will tell you that it's invalid. Right? If I even try on my calculator to go negative 2 natural log of that, so right, you cannot take natural log of negative numbers. Doesn't matter. Remember, the domain of logarithmic functions is strictly positive. The range of exponential functions is strictly positive, so one becomes the other. But anyway, so right there, you know, the graph of e to the x is this, and negative 2 is here. So it never reaches negative 2. Right? This is e to the x, and this is negative 2. So now it works. So no solution. So the only solution is natural log of 3. How is that? Does that make sense? Well, sure. I mean, this is really messy. This one tests you on almost everything we've learned in this whole class.
Makes sense when
Well, just ask yourself, what would Alex do,
you
and and then go from there. That's actually a valid. That's a valid learning technique. All right, so that's exponential equations. Logarithmic equations. There are a few types of logarithmic equations, just like when we dealt with exponentials. You have cases where you have the same base, those are nice. You have the cases that don't have the same base, but you can tweak it so they have the same base. That's also nice. And then we dealt with cases where the bases are different. Now, with logarithmic equations, the first type of problems that you'll see, and this is a very nice type, if you have a log base whatever of something equals a constant, usually something like that. Okay? So to solve these types of equations, when you have a single log on one side and a constant on the other side, the way to solve this equation is to rewrite in exponential form. Which means x equals a to the power b. Okay? So example, let's say we have log base 3 of 2x minus 1 equals 2, something like that. So you have a single log equals a constant. So right away, in order to solve this equation, just rewrite it in the exponential form. That means 2x minus 1 equals 3 to the power 2. Right? It's always the base raised to whatever's on the other side equals what's on the inside. Is that all right? Now that's a linear equation, isn't it? That just means 2x minus 1 equals 9. So then solve for x, add 1 to both sides. 2x equals 10. X equals 5. How's this? Did that make sense? Let's try another one. Log base 5 of 8 minus 7x equals 3. How do we go about that one? That's right. 8 minus 7x equals 5 to the third. That's a linear equation again. We can all solve that one, right? That means 8 minus 7x equals 125. Subtract 8 from both sides. Negative 7x equals 117. Is that right? 117. So then x equals negative 117 divided by 7. I don't know. Okay. What was that? Negative 714, whatever. How's that? That makes sense? What if I do this one? Well, I'll go back to the same page. 3 times natural log of 3x plus 1 equals 5. Now, plus 1 is outside the log, so just natural log of 3x plus 1. So the first thing we'll have to do is to isolate the natural log. So we want to get rid of 1 and then get rid of 3. You can divide both sides by 3. Natural log of 3x equals 4/3. So now we have it in the form of a logarithm on one side and a constant on the other side. So now we'll just have to rewrite it in the exponential form. Now what would that be? Right, 3x equals e to the power 4/3. So it's always the base raised to this. The base is e. So
Base C on both sides is
you can say that too. Yeah. If you think about that, if you do that on both sides, then the left side collapses to just 3x. The right side is e to the 4/3. Or just think about rewriting as the base to that power equals what's on the inside. Like you did the previous one. Right? You went base to that power equals what's on the inside. Same thing here.
okay, so
Base is e. Yeah. So then x equals e to the 4/3 over 3. What's that? You already? 1.265. Okay. Good. So again, these are the cases where you have a single log equals a constant. This problem started with something else. It was a little messier. So you had to do whatever possible algebraically to get single log on one side and a constant on the other side. Right? Okay. Let's try this one. Log of x plus log of x minus 9 equals 1. So we have 2 logs separated by a plus on one side and the constant on the other side. So far, we only know how to solve logarithmic equations that have 1 log on one side and a constant on the other side, right? That's what we've done so far. 1 log equals a constant. Here we have 2 logs equals a constant. But is there a way to turn 2 logs with a plus in between into a 1 log? Yes. We have the product rule for that. X times x minus 9 equals 1. So now we're back where we started, right? It's a single log equals a number. So if I rewrite this in the exponential form, the base of the logarithm is 10. So it is 10 raised to the power 1 equals whatever's on the inside. So it's the base raised to the other side of the equation equals what's on the inside of the log. So that gives me x times x minus 9 equals 10 to the power 1. 10 because that's a log base 10.
so you just multiply both sides by 1?
No, again, like you told me what to do here. It's the same thing. You take the base, you raise to the power, you get that. So you take the base, which is what? 10, you raise to the power, you get what's on the inside. right? So it's the same process. Or,
It's just easier to see it with numbers.
right, so that's why, you had problems with natural log and that one. But just think of that, there's a 10 in there. Now that's a quadratic equation. If you open up the parenthesis, you move 10 over, that's a quadratic equation. I can solve that one. X minus 10, x plus 1 equals 0. X equals 10, x equals negative 1. Are we done? I got the answer. Do both of these answers work? Well, what happens if I take x equals negative 1 and I plug it in there? Right, you cannot do log of a negative number. So that would be one of those extraneous solutions, so you kind of have to check here. And again, just make sure you don't have to check it. Just make sure you don't get negatives inside the log. Okay? So with negative 1, you're going to end up with both logs being negative, so it's undefined. But 10 works, so this is the only solution. This is the extraneous. So that doesn't work. Only 10 works. And not just automatically you ignore all the negative numbers. You just make sure that logs don't get negatives on the inside, because the domain of the log is strictly positive. Is that okay? What? That's, I said the exact opposite here. It's just make sure you don't get negative on the inside. Just because this x is negative, you can still get a positive on the inside. What if this was 9 minus x? So negative x works. Right? So just make sure that you don't get negative on the inside. Right. Yeah, that fails in both places. But as long as it fails in one, it just doesn't work. If the answer came out to be 3, it works in the first log, but doesn't in the second, so it just doesn't work. Log base 8 of x plus 1 minus log base 8 of x equals 2. So again, I have 2 logs on one side, separated by a minus sign, right? Well, there's a really nice way that I can turn that into single. Keep going, you're right. Over x, right? Right, so that's using the quotient rule, equals 2. So now we can rewrite that again in exponential form. So that's 8 raised to the power 2 equals what's on the inside. So it's x plus 1 over x equals 8 squared. So it is x plus 1 over x equals 64. Now how would you go about solving this one? Right, multiply both sides by x. So that cancels. You get x plus 1 equals 64x. Right, if you multiply both sides by x. Because you get rid of the denominator. So now it's again a linear equation. So subtract x from both sides. 1 equals 63x. So x is 1/63. And again, just kind of quickly check whether it stays in the domain, and it does, right? So you don't get anything negative from the inside. So it works. You don't have to check it. It will work.
So you just take 1x substance 4. Subtract that out. Oh wait, no, I see.
That's okay. Is that okay? So these are the cases where you have a logarithm equals a number. The another case that you will see, and this is what I already wrote on the board earlier today, is when you have two logs, log equals a log, same base, then that automatically whatever's on the inside has to equal as well. I wrote that already earlier, but just to show you an example, just trying to find one. Well, whatever. Let's say if you have, for example, log base 3 of 2x minus 4 equals log base 3 of x. If it's something like that, bases are the same, then automatically 2x minus 4 equals x. If bases are the same. If bases are not the same, then we won't even try that. You can do that one by graphing, kind of graph both, see where they intersect. But so here we go. Again, linear equation. So what is that? X equals 4. Right?
This is when you have a log on both sides.
Right. But again, it's a 1 log equals 1 log. Okay? If you have 2 logs equals 1 log, you can always turn 2 logs into 1 by using our rule. So for example, if we have something like this, log of x plus log of x plus 4 equals log of 12. See, here I have 2 logs equals 1 log. So again, I'm going to have to turn 2 logs into 1 to get it back into the form log equals a log. So that's using our product rule, so it becomes log of x times x plus 4 equals log of 12. And then I can use our rule. We have a single log equals a single log, then whatever's on the inside has to equal as well, so x times x plus 4 equals 12. So x squared plus 4x minus 12 equals 0. That's a nice quadratic. We can solve that quadratic just by factoring. X plus 6, x minus 2 equals 0. So x equals negative 6, and x equals positive 2. Do both of these work? Right. Negative 6 doesn't work, only positive 2 works. Because again, if you go back, negative 6 will give you some negatives on the inside, while 2 works. question? Yeah, but before we do that, the log of -6 is just undefined to begin with. So I won't be able to proceed. I mean, it works to solve this equation, but it won't work in the original logarithmic. Is that okay? Good. How about this one? This one is a little messier. We have 2 logs of 50 equals 3 logs of 25 plus log of x minus 2. What should we do first here? What do you think? Right. First, get rid of those constants, because our rule here does not have any constants in front. It just has to be pure log and a pure log. So yes, get rid of those first. So that's log of 50 squared equals log of 25 cubed plus log of x minus 2. And there are many ways to proceed from here, but, and again, you don't need to compute 50 squared or 25 cubed yet, but what would you do now? Okay, sure. Right, 25 cubed times x minus 2. Right? So then you have a log equals a log. So 50 squared equals 25 cubed times x minus 2. Right. That's the big thing. If this was, for example, 2, 8, and 10, then nothing we can do. They have to have the same base in order for us to start combining them. Actually, it would be easier right now if I just divide both sides by 25 cubed. It would be easier. No, I just ignore log, period. You cannot divide by log. Log is just 3 letters. It's just the name of the function. It's always log of something. What I'm doing, I'm using this property. When it's a log, same base, then I can just look at the insides. But I'm not dividing by log. So what's the left side, really? What does that equal to? What? Does it? Yeah. Right, it's 4 over 25. Right? You got 0.16? Yeah. So the left side, if you plug in a calculator or if you reduce it, it's 4/25 or 0.16 equals x minus 2. So solving for x now is easy. X is 2 and 4/25 or 2.16. But anyways, the message here is before you start adding logs, you have to get rid of the coefficients. You have to put coefficients back as an exponent before we proceed with anything like that. Is that okay? Well, in final, I have to give you something like that. So this is basically all that is covered in that section, just different techniques of solving. But if I give you a question like this, for example, 5e to the x plus 10 equals 3x plus 40. There's nothing much I can do with this algebraically. When you have a mixture of an exponential term and then a linear, right? Because the thing on the right is exponential, the thing on the thing on the left is exponential, the thing on the right is linear. So the only way I can solve this one is by graphing. If I graph this function, or these two functions, and see where they intersect, it will work. I mean, you can simplify it a little bit. You can subtract 10 from both sides just to make it a little easier. You can say it's 5e to the x equals 3x minus 30. Okay? Because again, before I even graph this on the calculator, I know 5e to the x is this. This is 5e to the x. Okay? 3x minus 30 is something like that. So line, right? They might not even meet, right? They don't meet when you're graphing. Probably not, because that the slope, yeah. But if I graph them, yeah, it looked like they didn't work. What was that? Foo plot? Like that? Yeah, here we go. Because look, if I graph 5 times e to the power x, see that one? And I have to go really like, and the other one would be 3 times x. Actually, I think I made a mistake. Oh yeah, that should be plus 30. That's better. Yeah, that's silly. That should be plus 30, right? So then it will work. Maybe in a few places. So if I go here, oops, 3x plus 30, here we go, right? So there is a solution somewhere here. I really have to zoom in. Because that, see, that exponential function is almost on the x-axis. See that? But not quite. That's one solution right there, right? We can find the intersection. We can trace, I don't know. Almost 10, almost negative 10, right? And the other one, is all the way up here. Right? So almost 2. So you can do those graphically as well. But we won't be able to do equation like that analytically. Okay, good. Well, that's about all in that section. We just did one section today. They're cover a lot of stuff in those. All right, so you still have 3, 4 due tonight. 3-5 not due till next week. And we have a test next week, don't we? What? Yeah, on the 20th. Excellent. Well, we'll be done learning next week, so it's all. I mean, we'll be done learning this week, so it's review Monday. Yeah, because we're gonna do 5, 6 on Wednesday, and this is just word problems. Yeah, yeah. Monday's review. I don't know yet.